Good morning, my dear students. Today we are going to see the definition of a limit point of a set, closure of a set, and closed set. We start with by presenting the definition of a limit point of a set in a metric space. Let x comma d be a metric space. Here capital X be any non-empty set and D be the metric defined on D, and A be a subset of capital X. A point small x in capital X is said to be a limit point of A if every neighborhood of small x intersects in some point of A other than small x. That is, B of x comma r intersection with A minus singleton x is non-empty. Here B of x comma r denotes the open ball centered at x and a radius small r, and B of x comma r is any neighborhood of small x. From the definition, we note that the limit point of A may or may not be an element of A. That is, the limit point of A may lies outside of A also. Next, we are going to see the definition of closure of a set. Let A be the subset of the metric space x comma d. The closure of A is denoted by A closure and defined as the union of A and the set of all limit points of A. That is, A closure is equal to A union A dash, where A dash denotes the set of all limit points of A. Next, the definition of a closed set. A subset A of the metric space x comma d is said to be closed in X if it contains all its limit points. That is, the set of all limit points is a subset of A. That is, A dash is subset of A. In other words, A closure is equal to A. Next, we are going to see few examples of limit point of a set and its closure. First, we consider x is equal to the set of all real numbers R, and d of x comma y is equal to mod x minus y. That is the usual metric on R. We are all known that the neighborhood of small x in R is given by the open ball centered at small x and the radius r is equal to the set of all y belongs to R such that d of x comma y less than r. By using the definition of d, we can able to find that the open ball centered at small x and the radius r is equal to the open interval x minus r comma x plus r. First, we take A is to be the set of all natural numbers. That is, A is equal to 1, 2, 3 up to etc. Now, first we are going to check that every element of n is a limit point of n or not. That is, first we take x is equal to 1, for example, is a limit point of n or not. Clearly, x is equal to 1 is not a limit point of n. How? We can find a neighborhood centered at 1 and radius 1 by 2 does not intersect with A except 1. That is, there is a neighborhood B of x comma 1 by 2 such that b of 1 comma 1 by 2 intersection with a difference singleton 1 is equal to open interval 1 by 2 comma 3 by 2 intersection 2 set 2 3 etc. is equal to pi. Here b of 1 comma 1 by 2 is equal to, by using this definition, x minus r comma x plus r is equal to 1 minus 1 by 2 1 comma 1 plus 1 by 2, that is open interval 1 by 2 comma 3 by 2. A difference singleton 1 means that remove singleton 1, remove 1 from A, that is A difference 1 is equal to set 2 to 3 etc. Clearly we can see that intersection of these two sets is empty, since the open interval 1 by 2 comma 3 by 2 contains the natural number 1 only. Therefore their intersection is equal to pi. This implies that 1 is not a limit point of A. Similarly, we can see that 2, 3 are not limit points of A. From this, we find that every element of n are not limit points of n. Next, we are going to check that every element of r minus n, that is n complement, every element of n complement is a limit point of n or not. For example, we consider small x is equal to 1 by 2. Clearly 1 by 2 is not a limit point of A. How? There is a neighborhood b of x comma 1 by 4 intersection with A difference singleton 1 by 2 is equal to open interval 1 by 4 comma 3 by 4 intersection set 1 2 3 etc. is empty. Therefore 1 by 2 is not a limit point. Similarly, one can able to find every element of r minus n is not a limit point of n. Therefore every element of r is not a limit point of n. Therefore the set of all limit points of n is an empty set. Therefore n dash is equal to pi. Therefore n closure is equal to n union n dash, which is equal to n union pi, which is equal to n. Therefore n closure is equal to n. Therefore n is closed in R. Similarly, we can find that the set of all whole numbers contains all its limit points. Therefore the set of all whole numbers is closed in R. Here also the set of all limit points of W, the whole numbers, is pi. Similarly, the set of all integers is also closed in R. For the example, take d is equal to open interval 0 comma 1. Here 0 and 1 are limit points of d. Since every neighborhood of 0 contains some element of d other than 0. Therefore 0 is a limit point of d. Here we cannot able to find a neighborhood does not intersect with D in some point other than 0. Therefore, 0 is a limit point. Similarly, 1 is also a limit point. But 0 and 1 are not an elements of D. Therefore, D does not contain the limit points 0 and 1. Therefore, D is not closed. Therefore, D is not closed. Next example. Consider E is equal to the set of all rational numbers. Here also, the set of all rational numbers is not closed in R, since it does not contain all its limit points, because every real number is a limit point of Q. By density theorem, for rationals and irrationals, we can find a rational number between any two rational numbers. Similarly, we can find an irrational number between any two rational numbers. Therefore, every element of R is a limit point of Q. Therefore, Q dash is equal to R. Therefore, Q does not contain all its limit points. Therefore, Q is not closed. The closure of Q is equal to Q closure is equal to Q union Q dash. Q dash is equal to R. Therefore, Q union R. Therefore, Q closure is equal to R. Similarly, there are so many examples in R exist. For example, this every singleton set is closed in R. Every finite point set is closed in R. Every closed interval in R is closed in R. Similarly, there are so many examples. Thank you.